Don, can I turn this over to you? Don is our one of our two vice presidents and program chairs. So he's been getting nice programs.
Okay, so tonight we're fortunate to have Stan Kurtz with us. Stan is a research professor at the National Autonomous University of Mexico, and he got his PhD in physics from the University of Wisconsin and worked on several occasions at Oak Ridge National Laboratory. He's currently pursuing his research at various research facilities, including the Very Large Array in Socorro, New Mexico, the Green Bank Telescope in West Virginia, and until recently, the Arecibo 1,000-foot telescope in Puerto Rico. He mostly studies high mass star formation, molecular clouds, and molecular late masers. But in recent years, he's also become involved in several radio instrumentation projects. And so the title of his talk is going to be a new radio telescope for Mexico. So with that, I'll turn it over to Stan.
Okay. Thank you, John. Good to see a number of familiar faces from just a month or so ago when we had the talk about the collapse of the Arecibo telescope. I'll start off my talk tonight by reminding everyone that I'm very informal about these talks, so please interrupt whenever you have a question. I'll try and be mindful of the chat window, but just go ahead and yell out, and we can stop to answer questions or explore other topics as you all desire. So the title is A New Radio Telescope for Mexico, but with the provision that it's actually a second-hand radio telescope, not completely brand new, but as you'll see, that's part of the interesting aspect of the project. When people think of radio telescopes in Mexico, hopefully these days, they think of the large millimeter telescope, which is this 50-meter dish on the Sierra Negra in the state of Puebla. Currently the largest millimeter dish in the world. The Nobayama dish is only 45 meters. This is 50, and plus the Japanese telescope is at an absolutely terrible site. I don't know, it's probably about 30 feet above sea level or something. This is 4,600 meters above sea level, so you can appreciate it's above most of the clouds in the background. And this telescope has a rather checkered history. I could easily give an entire talk just on the building of this telescope and corruption and intrigue and all sorts of other things that go along with it, but that'll be for another day. But one of the reasons that this telescope has been in the news, especially lately, is that it participated in the Event Horizon telescope that made the image of the black hole at the center of M87, which I am still not convinced is a black hole. I think it could be lots of other things, but one never knows about this. But the telescope I want to talk to you about today is not that big new modern millimeter wave dish, but it's a different one, which we call down here Tulancingo #1. It's located in the city of Tulancingo in the Mexican state of Hidalgo. It's about 75 miles northeast of Mexico City, 20 degrees north latitude, 98 degrees west longitude, and about 2,200 meters elevation. Not nearly as high as the large millimeter telescope, but as we'll see, this antenna will work at lower frequencies where the high elevation isn't quite so important. But these two antennas that you see in the picture here are landmarks for the people in Tulancingo. It's part of their city culture, and you can see license plates with radio telescopes on them, and it shows up in local artwork and so forth. They're very proud of their antennas. So the antenna that we wanted to convert was actually built in 1968, 67, 68 actually. It was just in time to broadcast the 1968 Olympics from Mexico City. So at that time, geostationary satellites were the cutting edge of telecommunications. So in Mexico City, they would film the Olympic Games, send them by a microwave link, the 75 miles up to Tulancingo, and then from there they'd go to geostationary satellites and around the world. So the first antenna was built just in time for the Olympics. You can see some of the construction pictures here below. It was a joint project by the Japanese and the TRW company, 32-meter diameter, a couple of thousand tons, and it's kind of hard to translate 1968 money into 2021 money, even for US dollars. But in the case of the Mexican peso, which has changed by a factor of at least 10,000 in that time frame, it's even rougher. But I would estimate that the construction cost at the time was the equivalent of about $20 million, give or take a few million. So this was actually they built the antenna, but it was the beginning of the Mexican telecommunications industry, the so-called Earth Station at Tulancingo. This was the first antenna that they built, Tulancingo 1. Later in 1981, they built a second antenna. I took this picture standing on a ladder about right here on the first antenna and looking over towards the second one. So it's a big site. It's over 100 acres. They have office buildings, a dormitory, kitchen, dining hall. There is even a helipad to land helicopters there. And of course the microwave links down to Mexico City and so forth. And I see that now that I think of it, I forgot to add a little something to the talk about why we are choosing to convert Tulancingo 1 into a radio telescope instead of Tulancingo number 2. And I'm going to anticipate, I'm going to explain in detail exactly what the conversion is and all of that. But I'll just take a moment now to point out that although number 1 was built in 68 and number 2 in 81, the first antenna is actually a much better one to convert into a radio telescope, because in the 1960s, they were just starting to build these telecommunications antennas. They didn't have a lot of experience yet, and they tended to overbuild them. They put in a lot more steel than they needed to. The structure was a lot more robust and strong than what really would have had to have been. And by the 1980s, they had learned how to cut the corners. And so the steel on this antenna, number 2, is a much lighter. The design is a lot more open, but also it had some intrinsic issues, so that when you leave the antenna parked for many years at a time, this antenna has lots of places where water can collect and then start rusting the structure. And this design didn't have those things. So we examined both of the antennas before we made the decision of which one to convert into a radio telescope. But the answer was very clear that the older antenna was in much better condition and was the better candidate to turn into a radio telescope. Excuse me. So the Earth Station continued to grow. Today, I think there are over like a dozen antennas or more of all different sizes, from just a few meters up to the two 32-meter dishes. I didn't put in any slides, and we'll just briefly mention there are a set of 5 7-meter dishes that were built as kind of an early attempt at the Motorola mobile cell phones. If you remember that kind of, I'm not sure fiasco is quite the right word, but Motorola had this plan with their Iridium satellites and providing cell phone coverage via satellite instead of cell towers, and it didn't work out so well. And there had been a similar attempt back in the early 90s by a different company, and they installed these sets of 5 antennas all around the world. There's some in South Africa, some in Australia. There were 5 here in Mexico, and they are still there in perfect condition. Each one has a storage container full of microwave electronics. When we first went over to the site, it was, I don't know if any of you remember the Star Trek episode where they're on a planet that's about to be hit by an asteroid, and Spock finds this, you know, alien control panel to activate a tractor beam to send the asteroid away. It felt just like that, because you walk into the storage container of 30-year-old electronics. There's a microcomputer. It booted up Windows, and we were able to control things. It was really an amazing thing. But those antennas, there are other stories about them, but I don't think I have time this evening to go into that. So the antennas, you know, they've been sitting a long time. They've had some damage. There's some rust in spots. Cement is decayed in the stairways. The lubrication system had oil leaks and so forth. But they were still in relatively good condition, although they haven't been used for quite a few years, because first of all, people are using fiber optics these days. And even before that, with better amplifiers and so forth, people didn't really need the 30-meter class telescope. You can talk to a geostationary satellite just fine with an 8 or 10-meter telescope these days. So both of the larger antennas have been sitting idle for a number of years. And this isn't unique to Mexico. There are antennas like this all over the world. And for at least the last 10, if not 15 years, various people have been involved in activities to convert these antennas into radio telescopes. And the one I mentioned particularly here is called DARA, the Development in Africa with Radio Astronomy. It's funded by the Newton Fund, which is an United Kingdom program with developing countries more than anything else, to develop collaborations between England and the developing countries and promote economic development, educational development, improve ties between the two countries and so forth. And in Africa, they were particularly interested in that because South Africa, down here at the tip of the continent, was one of the competitors and successfully competed for the Square Kilometer Array radio telescope, which is, you know, a multi-billion-dollar project being split between South Africa and Australia. But since South Africa had made such a big commitment to radio telescopes, they wanted to do human resource development as well as just technical development. They just didn't want to build a telescope and let it sit idle. And so they also had a very multifaceted approach, and were including local economic development, educational development, and so forth. And as a part of that, they wanted to convert some of these old telecommunications dishes, which you see in white, which are located all around the continent of Africa. And one of the first ones that they've converted is one of these three. My geography in Africa isn't quite good enough, but one of these three would be Ghana. So these antennas have been converted all over the world. Australia has practically a twin of the Mexican telescope. They look virtually identical. Let's see, this is the Ghana telescope. There's in Canada, the USA. The first one in Latin America that was converted actually is in Peru. Unfortunately, the people haven't followed through and to use it there. And another one, which I will come back to in a little bit in the talk, is the Goonhilly Earth Station in the south of England. They have quite a few antennas there. This was one of the most powerful Earth stations back in the 60s and 70s. And we are collaborating with people at Goonhilly on the conversion of the Mexican antenna. So there are lots of examples of people trying to do this. All sorts of different situations. In Uruguay, for example, they would like to convert an antenna. Theirs is about 10 kilometers from the ocean. So you can imagine the rust problems that they have on their antenna compared to what we have here in Mexico. Ours is in very good condition. So we joined forces with a group at Oxford University. You can see some of the team members here in the upper right corner in the dish there in Tulancingo. We took the Gore-Tex cover off of the feed horn in the very center of the dish. So there's on the upper left, you see the entire antenna. That little spot in the middle is covering up the feed horn. That's over close to 3 meters in diameter right there, as you can get the scale size with the people next to it. If you could follow the radio waves going down in here, you would hit a mirror and bounce into this feed horn right here. And this picture in the lower right is the old microwave electronics that's inside the receiver cabin, which you see here on the lower left. So you can't appreciate all of this. It was a nightmare of rectangular waveguide. Microwave engineers from the 60s were very ingenious about how to design their systems. But basically, we have already, in fact, torn out all of this old equipment. We hope to save it and build up a little museum at some point. And we will attach our new receiver on right here and then receive the radio waves coming out of the feed horn. So we launched the project. We got some local publicity for the politicians, which was their main interest in the project. We got some good publicity for them. Here's the front page of one of the local newspapers from a couple of years ago. And it really has been a nice impact, I guess you might say, for the community is very pleased in a way that that someone is paying attention to their antennas again. They're, as I said earlier, they're very proud of their antennas. And so they are quite thrilled that people are coming in to move them again and make them work as radio telescopes. To give you a little idea of the overview of administratively of who's involved in the project, the United Kingdom, through the Newton Fund, is funding about half of it at the level of $500,000 US. And most of that is going to receiver development. The other half is coming from the state government of Hidalgo through their City of Knowledge and Culture. So those are the two main funding agencies. In terms of the people actually doing the work, here in Mexico, the academic partners are basically me at the institute where I work at the National University, and the other main astronomy institute in the country, which is in Aoi. They are the ones who have the large millimeter telescope, by the way. And we also have a couple of other partners who are facilitating the process. The Mexican Space Agency is kind of a liaison in the whole thing. And then Telecom, which is a division of the Ministry of Telecommunications and Transportation, are the actual owners of the site and the antenna. So they're the ones who are giving us permission to do all of this. And in terms of the actual work itself, again, Oxford and I are doing the receiver work, but the state of Hidalgo has contracted with 3 companies. First, there is the Duans company. It's a French company with subsidiaries in Mexico and Australia, some other places. They're doing the drive system, replacing motors, cables, antenna control unit, lightning protection, and so forth. Cromas is a local company there in the state of Hidalgo. They're doing the painting, the cement work, cleanup, the less technically demanding part of the job, if you will. And finally, my academic partner at INAOI is in charge of the preventative maintenance on the drive system. And also he's doing an optical study of the antenna, the quality of the surface, and so forth. And I'll say a little more about that in just a minute. So these are the main 3 people who are getting paid to do work on the antenna. Myself and Oxford, we're doing it basically for free because all of our money needs to go into either equipment for the receiver or a little bit of travel money, which we can no longer use because of the COVID. So the first step was to clean the antenna. It needed a bath. And so my colleagues at INAOI got their team together of stalwart young people and climbed up the antenna and they washed it by hand. They had buckets of soapy water and scrub brushes and washed the entire surface by hand. Looked a lot nicer when it was done. But after it was cleaned, and really the reason for cleaning it was that in order to do the optical study, they needed to attach little targets, little plastic stickers that would reflect the light back for their optical study. And so after cleaning it, as you see on the left, they spent hours and hours and hours laying out these little plastic targets in a very specific pattern, which you'll see again in just a little bit as a prelude to their optical study. And the people at INAOI were also in charge of overhauling the lubrication system. This was also one of the first things to do because if you're going to move a structure that big, you want to be sure that the bearings are all lubricated before you start moving it. So one of the first things to do was overhaul oil pumps, replace seals, fix leaks, change the oil and everything. And so their team spent several weeks just working on the lubrication system and being sure that that was in top shape. They also cleaned up all the gears. Here's a before and after picture up above of one of the elevation drive gears with its little lubricating system. The gears actually were in excellent condition on this antenna. And in a sense, that probably isn't very surprising if you think about how they used the antenna. They generally looked at 3 different geostationary satellites. So all they would do is move back and forth a few degrees on the sky between these 3 satellite signals. So the use that they made of the drive gears was very light compared to what you would do with a real radio telescope that would be tracking a source through the sky all day long or moving from one source to another continually. So in that regard, we're in very good luck that the drive gears are all in good shape. thinking of the Duon's work and what they had to do, the old original motors still worked. We could have continued to use them, but it just seemed sensible since they were 50 years old, and they were actually more powerful than probably they needed to be. So it was decided to replace them with brand new motors. So there are here, I believe these are the two azimuth drive motors, and then elsewhere there are two elevation drive motors. And each one of these, I think, is about 10 horsepower. The older ones were 15 or 20 horsepower. The old encoders, which measured the position of the antenna in azimuth and elevation, really weren't precise enough for pointing a radio telescope. We need much higher pointing precision than you need to locate a geostationary satellite. And also they were just very obsolete technology. You can get much better ones today. You can get replacement parts for the new ones, not for the old ones. So all the encoders were replaced as well. And finally, the antenna control unit, the old one was inoperable. It hadn't worked for years. It had had cards stolen out of the rack. It was all 1970s electronics. So there was really very little point in trying to fix the old one. So they just built a new one completely, which you see here on the right-hand side of the image. So very nicely done, a very modern antenna control unit. So getting back to that optical study, the group from the Large Millimeter Telescope is the group at Inaoi that are the ones who did the measurements for us. For their antenna, since it's designed to work at millimeter wavelengths, it's much more demanding in the quality of the surface than this telescope will be, which works at centimeter wavelengths. So for them, this was like a walk in the park. First of all, it was a smaller dish at half the elevation with much lower precision on the surface. So it was kind of a day romp for them to do this. But they used a laser tracker here in the upper left to measure some parts of the system. And then in the lower right, you can see possibly there's a crane with a little crate suspended from it. There's a person in this crate with a camera. All the little white spots you see on the dish are those targets that the people were pasting on. They're basically, each one is a little corner reflector. So no matter at what angle you look at it, it reflects light back at you. And the idea is that they move the camera around to many different positions and take pictures in each one of them. And then some very fancy software puts all of these images together to construct the shape of the surface of the dish. And that's what you see here. So there are three main parts to the optical system that you see here. The big part is the parabolic dish, where all the targets are affixed. You see some other white points up here. This is the subreflector up at the focus. The support legs you can see here. And then, well, the idea is that the radio waves come in from space. They hit the parabolic reflector. They reflect up to the subreflector and then back down through that hole in the middle of the dish, which is right here. And below that hole is another mirror. It's just a big aluminum plate, but with a very finely polished surface. And so the radio waves hit this plate and reflect off at a 45-degree angle, and they come here into the receiver cabin where you saw the picture earlier, and we'll detect them with our radio receiver. So the three parts of the optical system that are important to us are first, the primary reflector, the big parabola, second, the subreflector, and third, this mirror that sends the waves over to the side. So it's important to have very accurate measurements of all three of those optical components. And we don't need to go into too much detail on this one. The top figure basically shows that the focus and the astigmatism and the coma, all of these are optical defects in any kind of optical system. They are not too bad. The scale here is in meters, so 0, 2 millimeters, 4 millimeters, 6 millimeters, and so forth. You can see where we really do suffer a little bit are the sphericity terms. So this is actually more optics than I can remember from grad school, but if you get out your old optics textbook, there are these Zernike polynomials that you can use to describe all of these defects in the surface, and in some cases you can correct for them. But probably the most interesting measurement of the surface for us to look at here are the deviations from the perfect parabolic shape. So the photogrammetry that they did of the primary reflector, you see here in this big image, this was taken when the antenna was pointed straight up at zenith. And that's where usually you would expect the best performance, and that's the case here. And the reason for that is largely that the forces of gravity are symmetrical when you're pointed at the zenith. When you start to tilt over to a different elevation, then you get some asymmetries in the gravitational loading, and you can start to get some more distortion. So those worst aberrations that you saw here have already been subtracted out, and what's left are just the minor imperfections in the surface panels. And the scale you see here ranges from plus or minus 5 millimeters from the perfect shape. So wherever you see a dark color, whether it's dark blue or dark red, those are the bad spots. The RMS here is just a shade over 1 millimeter, averaged over the whole dish. And if you point it down 30 degrees to a 60-degree elevation, then that increases to about 1.3 millimeters. It's pretty much the same places that are bad, although a few new ones show up. This spot here was okay at the zenith, but you can see it starts to get bad at lower elevations. Now, these numbers are kind of important for us because they tell us at how high a frequency we can use the antenna. Ideally, one would like to have the surface imperfections to be at the level of a 20th of a wavelength or less. And that ensures a fairly efficient collection of radio waves. If you start to get too much worse than a 20th, then the antenna becomes very inefficient and doesn't collect the waves very well. But you can still use it really at a 10th of a wavelength. And that's really interesting for us because 1.3 millimeters times 10 is 1.3 centimeters. And the water molecule has a very important transition at a wavelength of 1.3 centimeters. So I was really pleased when I saw these results because it means that although it won't be ideal, we will be able to use this antenna at 22 gigahertz where the water line is emitted. We'll have to build a new receiver for that, but we will be able to observe water. And that astronomically, that will be very important for us. So far, I've talked about the antenna and its conversion. I want to say just a few words about the receiver system, since that's what I'm working on the most myself in conjunction with the people from Oxford. Just to get things going, to do the commissioning and some early science and the original testing of the antenna, we're building a receiver at L-band, which will run from about 1400 to 1750 megahertz. We want to be down here at 1400 to get the hydrogen line at 1420 megahertz. And then we'd like to go up at least as high as 1720, because there are 4 spectral lines from the hydroxyl molecule, which are important astronomically. So if we have the full range from 1400 to 1750, then we can get hydrogen and the 4 hydroxyl lines all in our passband. And that will allow us to do quite a bit of interesting science. So we're working on this building this receiver now, heterodyne system. Well, these are all mini circuits, components. So it's not a real super sophisticated receiver, but it will serve fairly well. And at these frequencies, one can do pretty well with off-the-shelf electronics. So the signal will come through filters, mixers, more filters, amplifiers. It will finally be digitized, and then we'll process the signal with a FPGA, a field programmable gate array, that will make the spectrum of the signals that we're detecting. So it will always be helpful to have this L-band receiver around, because there are some things that you just have to have these frequency bands if you want to observe them. But the real interesting receiver for this project is one that we're building with the group at Oxford University in the UK. It's based on a design for one of those antennas at the Goonhilly Earth Station in Cornwall. This receiver will be at C-band, so it will cover the 4 to 8.5 gigahertz range. And most importantly, it will be cryogenically cooled. So it will be a very sensitive receiver, very adequate for radio astronomy applications. Unfortunately, we won't be able to cool it down at the outset. We have enough money to build the cold head into the receiver, so there will be the cryogenic apparatus here inside the doer of the receiver. But Mexico was supposed to buy the helium compressors that make all of this run for the cryogenic systems, and all our money got spent elsewhere. Well, we won't go into where all it went to, but I have some disagreements with people from the state of Hidalgo on that point, but we'll leave that for discussion over beers after the formal talk is over. To stabilize the performance of the system, we'll have a white noise source, and that will allow us to have very stable gains on our system, and which are necessary for radio work. If you're looking at a geostationary satellite and the signal level fluctuates by a factor of 2 or 3, you can compensate for that. It's no problem. But in radio astronomy, where you're trying to measure the level coming from the star or the planet or whatever, you need much higher precision than a factor of 2 or 3. So we need very highly stable gains in our electronic system. I'll comment briefly that the idea really was to have this receiver ready to go now. But when COVID hit, we weren't able to, I wasn't able to go over to Oxford to help with the construction of it. And so everything has kind of been on hold. But we are hoping that maybe by this summer, we'll have it finished and we can install it on the antenna. So once we have these 2 receivers on the antenna, what sorts of things can we study? Well, just a short list of the many that we can look at. First, I mentioned the neutral hydrogen line at 1420 megahertz. So when hydrogen suffers this spin flip, it emits a photon of 21 centimeters wavelength and falls in the L band. And since hydrogen is so abundant, we can use that as a tracer of clouds here within the Milky Way. We can use it to trace the spiral arms, clouds of gas within the Milky Way, how it's formed and its internal structure, the bar in the center of the galaxy, and so forth. And also other galaxies. You can study the hydrogen emission from them as well. So that's one of the first things we'll look at. Also, you can study highly excited atoms of hydrogen, helium, and carbon, which are fairly common in interstellar plasmas. So if you have gas in the interstellar medium that's been ionized, and that can happen either because of ultraviolet photons that are coming from nearby stars, or maybe if the gas is very hot, if it's been shocked and has reached hundreds of thousands of degrees in temperature, then just the physical collisions between the atoms will be enough to ionize them and pull electrons off from the atom. But then when those electrons fall back into the atom, when they're captured by the atom again, usually they're captured in very highly excited orbits. When we all studied basic physics, we had to calculate, the wavelength of light when the transition is from n equals 3 to n equals 2 and things like that. Well, here we're talking about n equals 160 or 300. In fact, they've even measured up as high as 600 and 700 for some of these atoms. So these are highly excited atoms called Rydberg atoms. The energy difference between the levels is very small. So the photons that are emitted are in the radio wave regime, and that's how we detect them with our radio telescopes. And finally, of course, these molecules are of great interest. I mentioned hydroxyl, the OH molecule, which has the 4 transitions at L band. Methanol is a very important, very interesting molecule. It's what you see here on the left. Although it's a fairly simple molecule, there are lots of different ways in which it can twist and vibrate and oscillate, and each one of those has a different frequency. And some of those frequencies emit maser emission. So again, like a laser, light amplitude, light amplification by stimulated emission, but in this case, maser, microwave amplification by stimulated emission. So very bright sources, which are fairly easy to detect even with a single antenna. So all of these different emission mechanisms we can use to study a whole raft of astronomical problems. Star formation, of course, is what I'm interested in, but you can also study atmospheres of planets, other galaxies, supernova remnants, pulsars you can do, although preferably at a little bit lower frequencies, but it would be possible to study pulsars as well with this system. So lots of astronomical applications. And although I won't go into it, geodesy is something that would be very interesting to do as well, for reasons that we'll mention a little bit later in the talk. So geodesy, using antennas from all over the planet to measure with very high precision the separation between radio telescopes in, say, the USA and Germany. And thus you can measure the continental drift, movement due to plate tectonics, how America is separating from Europe at a rate of 1 millimeter a year or so. Those kinds of measurements one can also do with this antenna. But for that, you need higher angular resolution. And that's one of the problems when you have a single dish telescope. It's one of the reasons that they aren't quite as popular as they were 30 or 40 years ago, is that in order to see fine details, to resolve very small angles, it's hard to do it with a single antenna because the angular resolution that you obtain just isn't quite good enough. And the solution to that is to use arrays of many antennas. So here's our couple of shots of the Very Large Array in New Mexico with its 27 antennas, each one 25 meters in diameter, not quite as big as the Tulancingo dish, but nearly so. And built actually only about 10 or 15 years later than Tulancingo. But in the case of an array, the angular resolution doesn't depend on the size of an individual dish. It depends on the separation between the individual dishes. And at the VLA, for example, where you can move these antennas along a railroad track, you can get a separation up to 35 kilometers between antennas. So you end up with a telescope with an effective diameter for angular resolution of 35 kilometers. Huge. And you get very high angular resolution that way. And in fact, you aren't limited to 35 kilometers. The Very Long Baseline Array is the North American interferometric array, which has 10 dishes from the Virgin Islands to Hawaii, and various dishes centered around the US. That has much longer separations, thousands of kilometers. So you can have a telescope as big as the Earth if you want. And in fact, even that isn't the limit. I have a collaboration with some Russian groups who put an antenna into space, the Spectre radioastron dish. Obviously not quite to scale here. The dish isn't as big as the Earth. It's only about 12 meters in diameter, but it orbits the Earth out to about 10 Earth diameters. So one ends up with the angular resolution that corresponds to an antenna that's many times bigger than the planet Earth. What you lose when you go to an interferometer is sensitivity, because you don't really have all of that collecting area to collect radio waves. So it's not as sensitive as you might like it to be, but it does have extremely high angular resolution, the best that can be achieved in astronomy.
Would you be interested in setting up a radio telescope on the moon specifically to assist in extending your baseline?
Oh, absolutely. That would be a great thing to do. It would, let's see, in fact, since you asked the question, it's clear you know the answer to what I'm about to pose. But I once had some fun with one of my basic astronomy classes trying to get an idea of the basic geometry of the solar system. So I would say, so it's how many New York cities will fit between New York City and Washington, D.C. or something like that, and people have kind of an intuitive feel for that and can guess. But how many Earths will fit between the Earth and the moon? So in fact, the moon would be quite a bit further away than this antenna is and would give a longer baseline. And of course, the stability of being on the lunar surface would be great. There are lots of other reasons to put one on the moon as well. You could greatly reduce the radio frequency interference. You wouldn't have to deal with the ionosphere and the troposphere of the Earth, which both affect radio waves. So lots of good reasons to put one on the moon, and it would be an ideal thing for an interferometer as well. Although, to be honest, I have not seen plans to do that. The plans I have seen so far are to put the additional antenna just floating in space. It would probably be at one of the Lagrange points. And just, it would unfurl, sort of, be a very flexible dish that would extend outward. But yeah, putting one on the moon would be great. So hopefully that'll happen one of these days. But first, before we go to the moon, let's just go to Latin America. Because if you look at this graph, these very long baseline interferometry networks, these collections of antenna arrays, are scattered all over the planet. But there's a big hole right in Latin America. So the USA and Canada have plenty of antennas. Europe has plenty of antennas. There's one antenna in Africa, down in South Africa at Hartbeespoort. East Asia has plenty of antennas, in Japan, in particular Korea as well. Australia has numerous antennas. So you have this big international network of VLBI arrays, but we're missing antennas in South America, Latin America, and Central America and Latin America. You can note Arecibo here. I'll try and carefully move my cursor without jumping ahead a slide. So this was the Arecibo telescope. For millimeter waves, the large millimeter telescope here in Mexico can participate. But most of the spots you see on this graph are actually for centimeter wave telescopes, not millimeter waves. And now that Arecibo is not functioning, the hole in this part of the planet has gotten even bigger. And people in Europe have noticed this fact already. In fact, the head of the European VLBI network, the EVN, had a telecon with me a couple of weeks ago to ask how we were doing with the Tulancingo telescope, because it could replace, in a sense, the Arecibo telescope in their network. It wouldn't be nearly as sensitive because it isn't as big a dish, but for VLBI, what's more important than the size of the dish is its separation from the other dishes. And so the fact that without Arecibo, you're missing a lot of these baselines, a lot of these connecting vectors between antennas. And so if we could put a point right here, that would replace very nicely the Arecibo dish, which hopefully Arecibo will come back. But in the meanwhile, we could serve with Tulancingo as well. And hopefully, what we would like to do is convert some of these other antennas in, see, I'll try and be careful. Let's see, Ecuador must be about here, Uruguay down here, Colombia here, the Peru antenna, which is already converted. So we could add easily another 4 or 5 antennas here in South America and really fill in this array coverage over the whole planet. And in fact, that's interesting not only for the astronomy, but again for the geodesy. Because if you want to know where your continent is moving to or from, you need to have a radio telescope on your continent to participate in these geodesy measurements. And so the fact that there aren't any radio telescopes in South America that are doing geodesy means that the geophysicists are kind of in the dark about just how much that continent is moving with respect to the others. And so they could greatly improve their geophysical studies if they had some antennas here in South America. So long term, we'd like to build a Latin American VLBI network, just as in Africa, if you remember all of the white dots that were in the African continent, they would like to build an Africa-wide VLBI network, and we'd like to have a Latin American VLBI network. Well, to close, I'll just hint at some of the problems that we have in making these projects work. I mentioned that our antenna is in really good physical shape. And when I got started in this conversion business, I thought that the most important thing was probably to have an antenna in good shape. And after several years of experience, I think that's not the most important thing. The most important thing is to have the support of your funding agency and your local political organization. Because if you've got good backing from the owner of the dish, and you've got good funding from your National Scientific Foundation, then you can fix all sorts of technical problems. But if you have a dish that's in good shape and the owners won't let you use it, or the people who are paying for the conversion are putting all kinds of obstacles in your path, then you encounter all of these political problems that are much more difficult to solve than the technical problems are. So I've learned along the way that I'd rather have a good political situation and a dish that's not quite so good than the reverse. But the other issue that I want to mention here is, once you've converted your antenna, how are you going to operate it? And that's an issue that we still have not solved here in Mexico. It's clear that for the first year or two, it will just be on a real shoestring budget, is expending as little money as possible for operation. Because with all of that infrastructure, it would be great to establish an observatory there. There's office space for 30, 40 people. There is space for electronics laboratories. You could have visiting groups in for conferences. There's dormitory space for visiting scientists. I mean, it's an observatory just sitting there waiting to be occupied. But somebody would have to pay for that. And we haven't found who will do that yet. And there are different approaches that have been taken. The dish that was converted in Ghana, for example, the federal government in Ghana said that they were going to create a radio astronomy observatory, and they are funding it. And it will be used for astronomy with the government footing the bill. In the United Kingdom, at that Goonhilly site, it's actually private enterprise. I think it was called British Telecom for several decades, and it was privatized by some prime minister a number of years back. And eventually the private enterprise that bought it from the government sold it to an entrepreneur. Well, first they rented it to the entrepreneur, and with the option to buy, and eventually the entrepreneur bought it, and he's doing great things with it. I mean, he's joined part of the Deep Space Network with NASA. He's found contracts in the telecommunications industry. He's used the infrastructure to set up high-performance computing centers. They're doing all kinds of great things there. It would be great to do something like that in Mexico, but there's no way that it would work to privatize the facility. That's just not a political reality here. It would be very badly seen to do something like that. So we're stuck with the communications ministry being the owner of the facility, but not really having any interest in developing it or putting money into it. And so we're out, scratching under rocks looking for ways to fund it and keep it operating as a radio observatory. So ideas are welcome for that. So I think I've talked for an hour here, which must be more than my limit. Let's open it up for discussion. Thanks very much for your attention.
Thank you, Stan. Got to unpin you so that the people will pop up. You know, there are some places around that do very well financially by tapping into the tourist trade. Rich folks that want to go to a unique place, they want to bring their kids, they pay a lot. And I've sometimes been to those places and helped people. I've never paid for various reasons. But I wonder if this could be, just as ecotourism is a big thing, I wonder if astronomy tourism or scientific tourism might be.
Well, we've thought about that, and that's part of the idea. I mentioned we'd like to save all of the old microwave equipment from the telecommunications era to make a little museum. And certainly there is plenty of infrastructure to build a science museum on the site, maybe with a special focus on radio and telecommunications. How much money it would make is a tougher call. If you drive 50 miles up the road to Pachuca, which is the state capital, they have a science museum already, and they charge an admission fee of about $3, I think, even less than that, $1.50, something like that. And I have not asked how many people go a year to that museum, but I guess you could make a little bit of money off of it, but not really enough to operate the observatory. We would like to do the museum and the astrotourism just as public outreach and human development. And I'm sure we could get a little bit of money off of it as well, but not enough.
Stan, there might be people who would pay to stay there. I have paid to go to PARI, Pisgah Astronomical Research Institute in North Carolina. It's a neat place. So that's
yeah, we've talked about that. Even with the large millimeter telescope in Puebla, I kidded the director there that he should point it at the zenith during a solstice or something, and put on a champagne dinner there in the dish and charge $1,000 a plate for people who want to absorb the cosmic radiation coming in from space. But yeah, those are good ideas. And we go back then to the political will and interest. If this Earth station in Tulancingo were being operated by an entrepreneur, you could do something like that. But since it's part of the communications ministry, I even have to ask for permission 3 days in advance and send the license plate of my car and what day I'm going to be there and what hours. It's all pointless, to be honest. I mean, it's leftover security from the day when this was an important part of Mexican infrastructure. And it isn't anymore, but it's federal government property, and so they guard it as such. And they're not, the communications ministry isn't interested in projects like that. So that's why I was really kind of disappointed that we couldn't follow the UK model, because if we could, we'd have the museum, we'd have the astrotourism. That would just be a no-brainer. If you go right now, you can go over to Cornwall and they have a visitor center there. And you can, I think eventually they want to be able to have people stay on site as well. I don't think they've accomplished that yet, but that's part of their long-term goals. They had a rock concert there a year or two ago. Had like 10,000 people come in for a rock concert. So when you're private enterprise, you have that kind of flexibility.
I have a question. Maybe I missed it, but I don't think you said anything about what kind of astrophysical objects it's interesting to study with this. Can you tell us a little bit about that?
Yeah, there are, I should actually bring up a different talk to show that, but the ones that I did mention specifically would be star formation, planetary atmospheres, galaxies, supernova remnants, and I think I stuck pulsars in there as well. But really, probably, well, what you have to keep in mind is that since it's a single dish, unless it's operating as part of an international array, it will have fairly low angular resolution.
Yeah.
And that kind of limits the things that you can study. But one that would be very interesting is these supernova remnants. So these are, you know, when a star gets old, explodes, ejects a huge bubble or forms a big bubble of ionized gas around it. And one of the astronomical problems that we still face today is that there should be a lot more of these supernova remnants than we see, because we have a pretty good idea of stellar evolution, how long the stars live and how many stars there are. So we can estimate how many supernova remnants there should be in the Milky Way. And we only see a couple % of that number. So where are all of them that we expect to see? And one good possibility is that they have expanded so big that you can't see them with a high resolution array of telescopes. You need low resolution telescopes to see big objects. And so one interesting application would be a galaxy-wide search for supernova remnants. I didn't put masers on the white list, but I did mention masers here in the molecule observations. And that's one that I'm particularly interested in because, well, it's related to star formation, which is my main area. But in the last 10 or 15 years, there have been a couple of very interesting discoveries related to these masers. The first one is that some of these masers are periodically variable. So it's well known that certain masers get brighter and dimmer sporadically. But about 10 or 15 years ago, we discovered half a dozen, actually now it's probably 15 or 20 of these masers, which get brighter on a very predictable basis. We can predict within just a few days of when they are going to turn on and get really bright, and then they'll drop down in their intensity. And there are at least 4, if not 5 theories now to explain what causes this. One idea is planets in a solar system. Another is a binary star system where each star has a stellar wind. And when the 2 stars get close to each other and their winds shock each other, that's when the masers get bright. That's another theory. But to find these periodic masers, you need years of monitoring because most of them have periods of like 200 days. So if you want to see 3 or 4 cycles, you need a couple of years of data of observing the same maser over and over and over again. And with really highly sought after telescopes like the VLA and ALMA, they don't want to give you time to observe the same source week after week after week. But when you have a dedicated dish like Tulancingo that isn't highly oversubscribed, you can afford to do that. So, you know, we could pick 50 of these objects and observe them once a week for the next 5 years. And we could probably double or more the size of these known periodic masers. And real quick, the other interesting discovery just 2 years ago, some of these star formation regions, suddenly the masers get like 100 or 1,000 times brighter. And the idea so far is that it's part of the star formation process, that when the star forms, there will be a circumstellar disk of material, and occasionally, so the theory goes, a big blob of that material will fall onto the star. And that's how you build up more and more massive stars. And the idea is that when this big blob of material falls onto the star, the masers get much, much brighter. And it turns out that the star also gets a lot brighter in the infrared. So you can detect it with other telescopes as well. So again, monitoring these masers to look for these bursts would be a great application.
See, I had a question. There was this recent measurement of phosphine gas on Venus, I believe using radio telescopes, quite a bit shorter wavelength than maybe what you're talking about. But is there a possibility of looking for other molecules, possibly outside our solar system like this, or is that too hard to resolve?
No, you can do that. And ALMA in particular is doing a lot of that these days. Very sensitive. And you said one of the key words there, higher frequency, or the shorter wavelengths. Because the number of molecular transitions grows almost like frequency cubed, roughly speaking. So at the higher frequencies, there are scads of molecular lines. Whereas at these centimeter waves, there are dozens of lines. So it's more appealing to do those studies with a millimeter wave telescope. But there are applications, and we certainly would try it. With a single dish, probably we would be restricted to the solar system. But even so, you know, that's fine. There are planets and moons, lots of things to see in the solar system as well. Now, if you had ALMA sensitivity, then you can start to look at nearby stars and stellar systems. And that, of course, is even more exciting. But definitely, we would try to look for a variety of molecules, both inside and outside the solar system. And again, since we have lots of time, even though we're not as sensitive, we can burn up hundreds of hours searching for these molecules.
What's the low frequency limit of your radio telescope there? Because the Cassegrain feed is going to have, you know, its diameter is going to, you know, throw a monkey wrench in the works there.
Yeah, no, a very astute question. And I kind of hinted at that when I said that for pulsars, you'd really like to have lower frequencies. For pulsars, you'd really like to be down around 400 megahertz or so, and we can't do that. I think realistically, probably 1 gigahertz is about the lowest we can go. So I don't think we really intend, we'll have this receiver from 1400 to 1750, and I don't think we'll even try to go below that. Although you could, and this is something that's really nifty at the Very Large Array, they have mounted dipole antennas in the dishes, which have a completely separate feed system. But then they have 27 of these dipoles with a nice metal back structure, and they do interferometry with those. I think it's called V-Lite, V-I-E-L-I-T-E. Very interesting, very powerful system for low frequency radio astronomy. Of course, for them, it's worth doing because they have 27 of them. We would only have one. So you might just as well build a little Yagi array to stand next to the big dish. So yeah, I think 1 gigahertz is going to be our low frequency limit.
Stan, I have a question.
Mm-hmm.
Thinking about fundraising and revenue opportunities. I am an entrepreneur. In fact, I was one of the first folks at Xilinx, who apparently you are somewhat familiar with. How quickly can your dish skew?
1 degree a minute.
Pretty slow. Okay.
Yeah, yeah. It's
not made to go fast. Yeah.
Yeah, exactly, exactly. Over at Goonhilly in the UK, they have a couple of small antennas that, wow, I mean, they are lightning fast. And you know, they bought those brand new, installed them specially for some of the contracts that they had for telecommunications.
Yeah, there's just a snoot full of LEOs and CubeSats, and sooner or later it's going to be a bandwidth bottleneck talking to the birds. If you could skew fast, you could track them and maybe pull in revenue. But
yeah, there's a lot of potential application there and good business opportunity. It's not my area. This private guy, the entrepreneur in the UK, is actually an electrical engineer, and you know, he spent years now flying around the world talking to satellite operators, NASA, and so he's really up on what the needs are. And in fact, we've talked to him about renting space in Mexico. What he would be interested in doing to fulfill some of his contracts, it would be useful to have a telescope at about the longitude of Mexico. And so he would be interested in, you know, renting, you know, 100 square meters and an electrical connection and an internet connection. And he would come and put in the antenna and just operate it remotely. But, and that's the sort of thing, again, if telecom had a little more vision, they could be doing that, but they don't.
Then what's the chance that you could get a 100-year lease on 2 or 3 of the 7-meter telescopes? They might be useful for that.
Yeah, that is an interesting option. We've talked some about that. In fact, one of the 7-meter dishes in South Africa is currently doing an all-sky survey to measure the polarization of the cosmic microwave background. I mean, cutting edge cosmology research with a 7-meter dish. And we've got 5 of them. So you could do things like that with, but you need to have human resource. Well, you need to have people with energy and time and money to make it happen. There are plenty of ideas, but to make it happen is.
Stan, I've got a question for you.
Mm-hmm.
Assuming I'm unmuted. Yeah, so you mentioned that there was a science museum about 50 miles away. Have you considered doing some kind of an educational program, either in conjunction with them, or maybe is there a university in the city there that you could do some kind of an educational program with?
There are multiple universities in the state, and one of the things on my list to do is make contact with them to try and develop contacts and so forth. How can I say this politely? The Mexican education system isn't maybe quite as robust as the US system is. So at the state level, we wouldn't get anything out of the state universities. They really don't have anything to offer us.
I thought maybe it would be a way that could get the communications ministry off your back. If they saw you were working with the university doing educational programs, maybe that would free you up to be able to.
Well, absolutely. It's something we need to do because the state government would like that. It looks good to the governor if his state universities are involved in the project. And so I really want to get them involved. The problem is they don't have the expertise that we need. So it's really more like public outreach on my part.
You'd be leading them into it instead of them.
Exactly. I would be
bringing anything
leading
to
them.
you. Yeah.
But
Okay.
but it's an important thing to do. And what I would like to do is get more people involved. Like at my institute, I'm really the only person who has any interest in hardware, radio telescope hardware. But there are other people who might be interested in the educational aspect or the museum or the public outreach. And so what I'd like to do is get some of those other people involved, and then they can cover those bases while I concentrate on the receiver and making the telescope work.
So what happens when you're trying to put together these things, and instead of the personal contact, which is important anywhere, but maybe more so in the Latin countries, when that's replaced by Zoom sessions?
Yeah. I'll be doing, sir, up to now, I mean, with the Oxford group in the UK, we have a weekly telecon. We have occasional telecons here in Mexico, but that's part of our organizational problem here with these different parties involved and not necessarily getting along that well with each other. We have very periodic Zoom sessions, and they are often more contentious than constructive. But yeah, for making the contacts with the universities, I should be trying that. You know, that would be a way to get started. And also other interested parties. There's a young couple in Guadalajara, so about a 3-hour drive from me, that I think they would be interested in participating in this project. So I need to start organizing Zoom sessions and get people on board.
No, I didn't ask that to try to get you to do more work. I was just expecting it's quite a challenge. And I wonder if there was some way of building excitement, even in the days of not personal context. I just got to see what your answer was.
Yeah.
I think what you've done there is a nice model for exporting to other places too.
Certainly, that's something that should be part of the project, because at some point I would like high schools and colleges throughout Mexico and elsewhere to be able to log in on over the internet and run the telescope. And so, I mean, that was something that will intrinsically be done via the internet. So there's no reason we couldn't get started with that now. To some extent, it goes back to the funding issue. My problem with the state government is that, well, this project should have been funded by the Mexican equivalent of the National Science Foundation. And had it been, I would have been in control of that part of the money, that pot of money. And I would have hired a project manager. I would have hired somebody to do this outreach work. I'd have a staff of 3 or 4 people working on all these different aspects. Because I've seen how NRAO does it. You know, they very organized in that way with different people covering different areas. But because it's the state government that's doing it, they're in control of the money and they have no interest in that. You know, they have their own agenda. But, you know, if it were a well-run, well-funded project, there would be a person whose full-time job would be what you just described, David.
Do we have more questions? One thing we probably will do is we'll finish up by going to people doing astrophotography, maybe Ted and Don. But if we have any more questions, I don't want to cut somebody off.
I have one more bit of input for you, Stan. So Bruce and I, through Sarah, we have access to time on, I think it's a 20 meter. Is that right, Bruce? That Steve has set up for us? I don't know how much revenue there is in that, but as you said, it's part of your technical infrastructure anyway to control and downlink the data from your dish. I don't know if, again, there's money in that, but I mean, having access to a dish for a reasonable amount, that would certainly be good for Viva La Mexico. And I'm sure you could go international as well.
Yeah, good point. We should explore that option of selling time. We had the original state university participation. They wrote up a business plan, and they thought we could sell time for, I think, $2,000 an hour. I estimate that maybe $200 an hour would be more realistic. But even that, you can pay for a new receiver that way.
10 grand a week.
Yeah. But then you will need to have an operator then probably, and well, maybe not. Have to look into it. Good ideas.
Earlier in the talk, you said something about, you had some questions about the imaging of the black hole in M87. Could you say more about that?
Well, yeah, I shouldn't give them too hard a time. That actually was a very impressive result that they got. I think I've seen that a little bit up close. There's one researcher at my institute who's involved in that, and the Mexican telescope. And one thing that's very clear to me is that the leaders of that project, there's one in the US and one in Europe, they are modern scientists who know the value of public relations. And they have hyped that to the max. I'm not saying it isn't good science, it is, but it has its fair share of hype as well.
Public imagination's awful important.
Yep. Yeah, and it's inspirational. It inspires kids to go into these fields, so it's worthwhile. I don't mean to give them a hard time about it. Well, I'll tell you, part of the reason it gets under my skin is because the guy I'll share a little local gossip with you. The local researcher who was involved immediately applied for the Mexican National Science Prize. And I was the academic secretary at the time, and so I was in charge of all the paperwork. And in the draft of his letter that we submitted, he wrote the rough draft, and then I edited it. He put in that it was clearly the most important astronomical discovery in recent decades. Now, wait a minute. Exoplanets, gravitational waves, again, hype, but worthwhile stuff, very worthwhile stuff.
I got a question about all these sources that you cannot monitor because you've got one dish. All the masers, for example. Anyway, I'm sure you've gone to a really, really nice approach to save every RF photon that comes in. It's very efficient, but I work at it a different way. Maybe you're throwing away 1,000 times as much as you're saving, because out in front of the dish, I'm not sure how good the image is, but you don't just have one focus. You have one focus for one source, the source on the axis, but you have other celestial sources imaged at different points. And if you put up a subreflector, I've been thinking about this. It seems to me that you can redirect that image out in space in the focal plane of the primary to different places, such as places on the dish. So if you wanted to monitor 10 masers, you would put, it's sort of a dynamic situation. Let's say 5. You could move them around, have 5 receivers that you could place. Does anyone ever try that?
Yep, great idea. They beat you to it, David. Green Bank, for example, at K-band has a focal plane array. I forget how many receivers they have in it. At millimeter waves, they're actually up to thousands, I think, in the most modern ones. So they're actually, I mean, the cutting edge here is more like a microwave CCD, if you will, that you will take a picture of a region simultaneously. And obviously, as you go to lower frequencies, each individual feed horn gets bigger.
Yeah.
And so at centimeter waves, I forget it. I think at Green Bank, at K-band, it's at least 7, but it might be 20 or 30.
Are you saying like a matrix of feed horns? Is that the idea?
Yes,
Okay,
exactly.
okay. Wow, I didn't know they could do that.
Just a rectangular array of feed horns tightly packed together, and they're all in the focal plane of the antenna, and each one is looking at a slightly different position on the sky. And so if you've got 20 feed horns, you're looking in 20 places at once, 20 times faster.
It's nice to be able to put them in the right places, so you don't have of your, say it's a 10-bit and you have 100 pixels or 100 elements. You're not using all those. It'd be nice to be able to move them where they are needed.
Ooh, now that's, I don't think anybody's tried that. But.
You know, everybody's got, not everybody, a lot of people have 3D printers around and they have XY positioning.
Mm-hmm.
Anyway, thank you, Stan. That's fine. This is really very gracious of you, Stan, to talk with us about this. And,
I'm glad to. You're a good group and always have good questions and comments, so it's fun to talk with Orion.
I think we just opened it up to more questions for you, as well as astrophotos or new SETI discoveries, which I'm always fascinated by. Keep looking for them.
Well, I have astrophotos that I'm dying to show people.
Go for it, Ted. We've been missing you with the
okay. Because I've been looking at these for 5 or 6 weeks and I haven't been able to show it. I sent you and Don, I think, these things. All but one of I've got 4 photos to show you of the Rosette Nebula in Monoceros. And what I've done is I've taken long exposures of it in hydrogen alpha and also in the other 2 wavelengths that are used to make up the Hubble palette, which are oxygen 3 and sulfur 2. I've had a sulfur 2 filter for a long time, but I've never tried to use it before. And I just playing around, I hit on a trick that really brought out a lot of detail in the dust clouds in this nebula. So let me try and show you the hydrogen alpha one first. It turned out the trick was just having long exposure frames instead of my usual stack of 104-second frames or 8-second frames. I said, okay, well, let's try 15 seconds. It looks like going from 4 to 8 improved things. 15 normally is you get tracking, but with my new mount, my GCX mount, that's not a problem anymore. And I use PhD2 guiding, so I got things pretty much locked into position. And the stuff just jumped out of the image. It was incredible. So
are you essentially using a palette then where instead of RGB colors, you're using a palette of molecular lines? Is that?
But I haven't done that yet. That's what people do. They
Ah.
use a hydrogen alpha image, an oxygen 3 image, and a sulfur 2 image.
Yeah.
Obviously, those are monochromatic. And they map them into hydrogen alpha, I think, to red, oxygen 3, which is green, they map into blue, and sulfur 2, which is a deeper red, they map into something else. And so you get a fake image that the public just loves because they're beautiful and multicolored and everything, and they look like they should. So they're much more beautiful than reality. But anyway, it's a fun thing to work on. And so I thought, well, I've got the 3 filters. Let me find an object that has a little bit of each one, and so I can work towards doing this. So I've got the 3 pieces. If anybody is set up to do this, to make a Hubble image from 3 monochrome exposures, I'll send you mine immediately, because this would be a simple exercise. They're not exactly the same field. Things drift a little bit from one night to the next, but they're pretty damn close. So it shouldn't, and they're the same size, so it shouldn't be too hard to superimpose them. So anyway, let me show you what they actually look like. Do I do share screen here?
You have that permission, I think.
Okay. Has it appeared?
Wow, that's nice.
Oh, it has appeared. Good.
Beautiful.
And you can see the pointer, right?
Yep.
Yes.
So this is the Rosette Nebula itself. There are a number of tiny little features you can see, really well defined. I was amazed at this, really well defined dust clouds, little points on the edges of them here and there. And some of these features have names, like this is the elephant's trunk, this bit here that sticks out. And this region here is where this thing is about 10 million years old, I think, where you've managed to form a number of bright hot stars down inside. It's an emission nebula. And you can see these stars have just blown away the dust that was in the central region. And they're now illuminating, I forget which of these 2 is the main spotlight, but they're illuminating the dust clouds all around. So you get, because there's a lot of free protons here, you get a lot of hydrogen emission seen, and so that's why there's a strong H-alpha line. Now let's see.
Did you have a scale? Do you have a scale here in terms of angular degrees or
yeah, it's well, let's see, it's about 4,000 pixels by 2,000 pixels, and a pixel is about an arc second for me. So I think this is roughly a degree. You know, the full width or full length is roughly a degree. I didn't work it out.
Thank you.
Sure. So let me see, how do I get rid of that? Oh, one of the things I read about when I looked at other people's images is they talk about the red skull visible in the Rosette Nebula. And I didn't see a red skull. I thought, this is such a good image, surely it'll show up. And I just found it recently. You have to zoom in on this region and flip it over. So let me show you the red skull.
Oh, there it is, yeah.
Yeah, but it helps if it's right side up too. So here's, oh, damn, I'll have to.
It looks like a face. I see it.
Have to reshare the screen just a second.
Ted, if you share your desktop, it should be easier for you to switch between.
I know, but if I start playing around, I mess everything up. Let me do simple things that I'm pretty sure work. So here comes, so there's the red skull, all right? You can see it's, these were the 2 bright stars in that star cluster, which is NGC 2244. And here's the red skull. It's obviously an alien skull because there's some sort of bone flange that sticks up here. So I thought that was an especially nice image.
Neat.
And I'm actually amazed at the amount of detail I got in this picture too. I guess it's from having a good mount finally. Okay, so what's the best way of getting to my next image? If I throw, I'll just move this one out of the way and open up the next one. How about that? Let's see if that works. So this is oxygen 3, the same region.
But you have a monochrome camera that you're adding colors to?
No, it's a color camera.
It is colored, okay.
So all I'm doing is just putting the filter in it, so it's recording, trying to record everything, but all it's got is that one oxygen 3 line in this case. And if you go back and compare this, so here's the skull region again. And there's that elephant's trunk. So you can see some features that were the same as in hydrogen alpha emission. But there's a lot of brightness down here in the hydrogen alpha emission that doesn't show up at all in oxygen 3. And this one has, I think, even longer. Yeah, these are 30-second frames, 60 30-second frames. So the last one was.
Ted, what are the streamers towards the right side, left side of your screen? You see these stars that look like they have cone shapes coming out of them, all the way. Yes. Yeah, right there. What is that? Do you suppose?
I think that's a bizarre artifact from data transfer. I've forgotten what the name of it is, but.
You don't think that's part of the actual nebula, then?
No, I don't.
Okay, I wasn't sure. It looked like there was a couple of them that have streaks like that over there.
Yeah, and there's another one coming up next that's sulfur 2, where it's really clear, and there it's just obvious this is some wacko artifact. You know, it's something about data transfer when you got USB 2.0 instead of 3.0, which is what I've got, and so slow data transfer for some reason gives you fake features in the images.
Well, and I suppose it could be something about stacking when you have an object that's right next to the edge that's in some of the frames, maybe and not in all of them.
Maybe, but on the other hand, all these little point stars are in a good place.
Yeah,
if you blow them up a long ways, you don't see any evidence of duplication of the stars. So I think well, that's my guess. It's just because I haven't upgraded my computer, so I'm still doing 2.0 transfers instead of 3.0. Okay, let me try and zap this and show you the sulfur 3 image. Now this is my sulfur 2 filter image. Off to the right, you can see that obvious artifact of rays coming out of a star. So that's another place where I think that's a data transfer artifact. So this is interesting because if you remember, this is in the hydrogen alpha image, this is a hollow region with stars in it, just that star cluster, that open cluster. And with sulfur 2, it looks like you see some glow in there. But over here, if you compare this with the hydrogen alpha image, the sulfur 2 line follows it suspiciously closely. So I've started to worry. And in fact, the wavelengths are pretty similar. Hydrogen alpha is 656 nanometers, but sulfur 2 is 672 nanometers. So those are only separated by about 15 nanometers. And the resolution, the full width half max of these filters is about 7 nanometers. So I think I'm getting feed through of hydrogen alpha. And I worked really hard in this. This is the longest these are 60-second exposures, 30 minutes altogether. But I think I'm just seeing feed through from the much brighter hydrogen alpha light. I suspect I don't really see much sulfur 2 at all.
Why don't you do a subtraction, Ted? The 2 images. Can you do that?
I don't really have any good software for doing things like that.
Rob and I used some software a while back that was capable of doing interesting things like that. Did you know, Rob, if we can put in Ted's images and work with them?
On what program are you thinking of?
The micro observatory program that we used.
Oh, yeah, I think it does have those functions. It was
they had the functions
software.
Yeah, you could just use GIMP. Just a basic GIMP. You just
take thanks, Rob.
Yeah, you GIMP does that. Images and you can just say take these 2 images and subtract them.
Does GIMP let you do expansion and so forth to register them?
Oh yeah. Sure.
Oh, good.
Yeah, you can do keystone registering too. So there's all sorts of capability. GIMP is almost as good as Photoshop these days.
Yeah, you do Linux, don't you, Ted?
I used to. I've got a Linux box.
Yeah. I think GIMP is.
Well, GIMP is
everywhere.
On platforms.
Yeah, it's cross-platform now.
GIMP on Windows and Mac.
Absolutely.
I use it. I do it all the time.
Okay, well, I need to talk to somebody about how to do this, or encourage somebody else to try to superimpose a couple of images. If you could just send me an email if you want to play with these, or better yet, I'll send them to David, the complete set, and anybody who wants them can play with them.
I'd like to have them for the edit anyways, but I'd love to give that a shot. I think I still have access to Photoshop for the rest of the month.
All right. So
Yeah.
one set to Rob.
Yeah, I'll take it too. I'd be curious. I'd like to try to do some alignments.
Who said that?
Rob Scott.
Rob Scott. Yeah, I've got Rob's address, and you can send it to me, but I'll send you Rob's email if that's okay, Rob. You want me to?
Yeah. That's just what I was going to say. Just
Yeah.
Okay, and I'll add a little bit of text explaining the details of the exposures and everything. Oh, this nebula is 5,000 light years away, so it's quite a ways out. I have one more image to show everybody. This is just.
By the way, Ted, I would say
candy.
that real quick. That last image that you had, I really don't believe you have a data transfer image problem with that star off the side. That actually looks more optical because of the way the rays are coming out. If it's data, it's going to be a lot more linear, basically going across or up and down. Those angles off those rays seem very strange for being data, especially since they're nowhere else in the image.
Okay, I'll send it to you. Stay it for a while and let me know what you think. Because
I'll take
Well, also, I think dark current tends to do things like that.
that's what I was trying. That's the phrase I was trying to remember.
Dark current.
Dark current.
What is that?
Well, that's what I thought was due to noise from data transfer.
Yeah, well, it's noise in the sensor chip when it's being read, I think.
Yeah, it also can be heat. It can be, what can happen is you can have a hot part of the camera off a chip off to the side that's basically radiating IR on you, and it's just picking up the extra data. So it's more likely in your hardware than a data transfer issue, but you can subtract it out. And I think if you, as Don suggested, you may be able to take it out by doing dark current subtractions. So,
Okay.
or dark.
So one quick eye candy image. This is the last one I've got. This is Procyon. I post astro images online so my old high school friends can see these things. They just love things like this, where there's one bright star in the middle. And some of them are Christians, so if there's a cross in the middle, they like it even better.
This is
All the better.
Maltese cross.
And I also give them a text description. So I say, this blue thing you're seeing, this is not the star. Procyon is actually an F5 or something like that, bright main sequence star. But anyway, that was just sort of a pretty eye candy kind of image, I thought. One neat thing about Procyon is it's fairly close, and it's in roughly the same direction as Sirius, which is also fairly close. So you might wonder, are those guys lucky? Are they closer together than 4.5 light years? And if you plug in the numbers, they're actually 2 light years apart. So if you want to point to, if you got astronomy students and they say, where in the sky are 2 stars that are really close together, it's Procyon and Sirius. Because I once typed in coordinates of the 50 nearest stars and had it run matching to see which ones were closest, and I found several that were 1.9 light years apart, and they were obscure. Procyon and Sirius are also 1.9 light years apart, so they're not obscure at all. So it's easy to see. All right, so that's my set for tonight. I'm glad I finally got to show you the Rosette Nebula images.
It's great. The students never. I don't either look up in the sky and know how far apart objects are. So I got the students one year to produce constructions where they mounted the little beads representing the stars on plastic sticks, and they actually developed their positions in 3 dimensions in space. And you can see a constellation is really pieces are scattered all over.